So welcome to the last part of Lecture 9, Part 4 for today for Math2R03. And we've been talking about looking at the set of all linear maps between two vector spaces. And what I want to do is kind of help you kind of understand what we're doing here by looking at what we did in Math1B03, but under the lens of what we've just talked about. So in Math1B03, we were looking at, say, our vector space was normally Rn, and our second vector space would be Rm. And we did see this sort of fact here. We didn't use this notation of script L, but we did see that if you have a linear map from Rn to Rm, that you can rephrase that this linear map, there had to be some sort of matrix A such that A times the vector x was the same thing as taking t and evaluating it at the function x. So any linear map really came from an m by n matrix. Okay. So really what you should be thinking about is you have your vector space R and Rm, and you're looking at all the linear transformation or linear maps from Rn to Rm, and somehow you're identifying the set over here with, and I'm using the notation of our textbook, this is the set of all m by m matrices. So how this map works, right, is you take a linear map and you associate to it the matrix A that you get that describes the map from Rn to Rm. So what you should think of is that this set here is the same. Now we don't have really a good notion of sameness. Yes, we will kind of explain this later on, but this set here is really the same as the vector space of m by n matrices. So one way to think about what we were doing in Math1B03 is we were looking at the set of m by n matrices. But under what we've been talking about today, what you're really looking at is you're looking at the vector space of all linear transformations from Rn to Rm. And so when we're doing today's lecture and we're introducing this new set, and I'll go right to the beginning here, we're introducing this set here of all linear maps from V to W. What we're trying to do is generalize, instead of looking at matrices, we're trying to look at the set of maps. So Math1B, we're very concrete when we're looking at matrices, but really what we're doing, if you take a different perspective, is we're looking at all linear maps from V to W. Okay, so that's one way to think about what we were doing in Math1B03. Okay, so think about maybe this set and this set here as kind of generalizing the set of m by n matrices. Okay, so that's kind of how maybe will help you understand what we're doing here. A couple other things just to kind of wrap up for today's lecture, because it will be kind of useful for later on, is the notion of the product of two linear transformations. So if you have a map T going from U to V and a map S going from V to W, the product of S and T is the map that goes from U to W, is the map that goes first, is the product, sorry, excuse me, it's the map that goes from U to W, where we take a U and we evaluate it by first plugging into T and then plugging into S. Okay, so here's kind of like the standard picture here. Here would be my vector U, and it gets mapped over here to TU, right? So this is my map T, and then this map gets over to the vector space W and goes STU. And what we're doing here with the product is we're defining the map ST to be the map that kind of bounces through these vector spaces. Okay, so another way to think about what a product means when we're taking linear maps is product is just another way of saying composition. So when our textbook talks about the product of two linear maps, they really mean the composition of two linear maps. And the final slide page here of my lecture here is just kind of describing some of the properties of products, but they really just are kind of the properties of composition of functions. right? Because I can take T2 and T3, do those first, and then stick it into T1, and it's the first thing. It's the same thing as composing T1 and T2, and then doing T3. That's the associative property. IV is going to, I'll write this out, but IV is the identity on V, and W is the identity on W, and this is equal to T, where IV is the identity map from B to V, and IW is the identity map from WW, okay, our identities. Okay, so if I take a function T that goes from V to W, and then, or U to, goes from U to V, and then I stick it into this function, it's the same thing as just doing the function T itself. Okay, and then we have this distributed property that holds for the product of transformations. We have S1T plus S2T, and then we have ST1 plus ST2. Okay, so these are kind of the properties of products, which is something that you would have seen before. Okay, so here's a little comic here. Today we actually started to see some matrices. I know this is linear algebra. You expected to see some matrices, and we're starting to see them kind of in the previous slide, but we're seeing them now as from a different perspective. We're looking at all linear transformations from a vector space to another vector space. Okay, so some of our key ideas here for today is we learned about linear maps, and then probably one of the more important things that we learned today is the vector space consisting of all linear transformations or linear maps from V to W, and we learned about the products of linear maps. So I think that's it today. Maybe I'll draw like a little dinosaur here, and he'll say goodbye, and there's my sad little dinosaur. And I hope you have a good day and you're enjoying the lectures. And again, as always, if you have questions, we have a discussion board set up for this course, so you can send them to them or send me an email. Okay, have a great day. Bye.